You have the concentration of EDTA from the label of the solution. Now, the volume of hard water in each sample is 25 milliliters. You were using the burette to transfer that volume into each Elmer flask to prepare your samples. That volume converted to liters is 0.025 liters. The volume of EDTA is the volume that you're using in each titration. So you're titrating your sample until it changes color to a very light blue. And when you see the color changing, you have to record the volume of EDTA that you're using. So if your initial volume is 0 because your burette is filled all the way to 0, and it goes down to, let's say, for example, 20, your final volume is 20, your initial volume is 0, which means that you're using 20 milliliters of EDTA in that titration. To calculate moles, not just moles of EDTA, but whenever you have a molar concentration for a solution and a volume, you can calculate moles by multiplying your volume in liters times the concentration or molar concentration. So you do have the concentration of EDTA that you copy from the label. It's up here. And you have a volume of EDTA, which is the volume of EDTA that you're using in each titration. So that volume of EDTA in liters times the molarity of EDTA will give you the moles of EDTA that you're using to titrate your sample. So for number 4, what you're calculating is just the average. So whatever number of samples you did in your titration, if you did 2, you're adding the moles of EDTA in your first sample plus the moles of EDTA in the second sample. All of those numbers added together divided by 2 will give you the average. If you did 3 samples, and then you need to add all number of moles, moles of your sample 1, moles of sample 2, moles in sample 3, all of that divided by 3 will give you the average. In the case that you had to do 4 samples, then you have to add all the moles of your 4 samples, moles of EDTA for your 4 samples, and all of that divided by 4 will give you the average. Now, from number 5, we're looking for the number of moles of the ion of calcium. So you're titrating your sample to determine like how much the concentration of the ions in your hard water sample. So the reaction between EDTA and the metals, it's 1-to-1, which means that any number of EDTA that you're calculating is the same number of moles of the ion that you have, because the reaction is 1-to-1. So for the moles of calcium plus 2, the ion of calcium, what you have is the same number or the same average number of moles that you calculated in number 4. The moles of calcium chloride is also the same number. Look, when we calcium carbonate, sorry. Calcium carbonate, when it dissociates to give you the ions, you have 1 ion of calcium, 1 ion of carbonate, which means that every mole of calcium is coming from a mole of calcium carbonate. So the same number that you have in 4 will be the number that you need in number 5, which is the same number that you need in number 6. Number 7, now you're converting moles to grams, which is a mass. Okay? So you want the mass of calcium carbonate. So to go from moles to grams, you have to multiply by the molar mass. So you're trying to convert the moles of calcium carbonate to grams of calcium carbonate. So you need to multiply the moles of calcium, which is what you have in number 6, times the molar mass of calcium carbonate. So that's not just moles of calcium here. That's wrong. That should be moles of calcium carbonate, because you're not multiplying that by the molar mass of calcium. Is the moles of calcium carbonate, okay? Which is what you have right there in number 6. So the moles of calcium carbonate times 100.1 grams per mole, which is the molar mass for calcium carbonate, that will give you the mass of calcium carbonate that you have in your sample. Mass of hard water. So you want the mass of your total solution. So you have the volume for your sample, it's 25 milliliters. Okay? So you can convert a volume to a mass or a number, whatever number you have in units of volume, to a new number with units of mass using the density as a conversion factor. So the volume of your hard water is 25 milliliters. So when you multiply that times the density of water, which is just 1 gram per milliliter, your unit of volume, milliliter, cancels out, and you get the mass, a number with units of grams, which is what you're trying to calculate in number 8. Then for number 9, you're calculating the total hardness in parts per million. So to do that, you're just dividing the mass of the solute, which is the calcium carbonate, what it's dissolved in the water, that's your solute. That number divided by the mass of the solution times 10 to the 6, which is a million parts per million. So the mass of the solute is what you calculated in number 7, is the mass of calcium carbonate. And then the mass of your solution is what you calculated in number 8. So you're dividing the number that you have in 7 by the number that you have in number 8 times 10 to the 6, and that will give you the total hardness. And the unit is parts per million. Now for the last part, we want to see like how much of your water hardness comes from the presence of your magnesium ion and how much comes from the calcium ion. Okay, so that's what we're doing. So you have a total hardness. That total hardness is the calcium ions and magnesium ions all together. So now we're going to look at them individually. So starting with number 1 right here, volume of EDTA, it's again the volume that you're using to titrate each sample. So you have your sample, it changes color to blue, and then when you see the color changing, you copy the volume from your burette, and you can determine how much EDTA you're using in your titration. To find out moles of EDTA is the same thing, molarity of EDTA times the volume of EDTA in liters. So molarity of EDTA is the number that you're copying from the label in your solution. And then the volume is how much EDTA you're using to titrate your sample, but remember that number has to be in liters. Molarity is moles per liter. Those are the units that you have in a molar concentration. So to cancel out the unit liters, your volume has to be in liters too. And again, the average moles is just adding the moles that you're getting for your sample 1, sample 2, sample 3, or whatever number of samples you're titrating. So you add the number of moles of EDTA for each sample, add all of them together, and then divide that amount by the number of samples that you have. If you have only 2 samples, so it's the moles of EDTA in the first sample plus the moles of EDTA in the second sample. Those two numbers added together divided by 2 will give you the average moles of EDTA. Now, the reaction between EDTA and calcium and magnesium, not just with calcium, also with magnesium, it's 1-to-1, which means that if you're using 10 moles of EDTA, it's because you have 10 moles of magnesium present in your sample. So the moles of magnesium in your sample is the same number that you calculated in number 3 for the average moles of EDTA. The moles of water hardness as we're converting magnesium to calcium carbonate because we're going to use the same molar mass. It's 1-to-1. So the same number of moles of magnesium that you have in number 4, which is the same number that you have in number 3, is the number that you have in number 5. Now, the mass of calcium carbonate again will be the moles What you have in number 5, which is the moles of water hardness in calcium carbonate, that number of moles times the molar mass of calcium carbonate, you're converting moles to grams, that will give you the mass of calcium carbonate. So the moles of hardness in calcium, which is the number that you have in 5, times 100.1 grams per mole, which is the molar mass of calcium carbonate, that will give you the mass. Okay? And that's the mass of the solute. Okay? Now, the water hardness due to magnesium, it will be the mass that you're calculating in 6 divided by 25 grams, which is the mass of the solution, times 10 to the 6, which is a million. That's why it's parts per million. We're converting everything that you have for magnesium to calcium because we calculated previously the hardness due to calcium carbonate. If we're going to do like a subtraction, you need to have the same thing. The total hardness due to calcium carbonate minus another one for calcium carbonate. It's not that it's still calcium carbonate, it's for magnesium. So you have the water hardness due to magnesium. You're calculating that one with the number that you have in 6 divided by 25 times 10 to the 6. The total hardness is what you have in part 1. Remember, you're doing these titrations here with the sample that we added the precipitating agent. So you have a total hardness that is due to calcium and magnesium. But when you added the precipitating agent, you remove the calcium ion from the solution. So everything that was left was the magnesium ion. So when you're doing these titrations, the EDTA is reacting only with the magnesium ions that you have. Okay. Now, the total hardness is what you have in your part 1, so you can just copy the same number. And then water hardness due to calcium in parts per million, that will be your total minus the one that you calculated here, number 7, which is the one for magnesium. You have in part 1, we did the total hardness. It's in calcium carbonate, amount of calcium carbonate, but since magnesium and carbonate, the relationship is 1 to 1, we can assume that that's a total. It's a calcium carbonate because we're using those grams, but we have the magnesium and the calcium all together. So for these titrations, you have only magnesium. We converted that also to calcium carbonate to have the same. So when you do the total minus this one here, which corresponds to magnesium, right? You're going to get the one that it's due to the calcium ion in solution. So the total, which is what you have in number 8 from part 1, minus the one that you calculated right here, the hardness that we calculated in number 7, that will give you the hardness due to magnesium. Okay? So that's all you need to do to have the parts per million of calcium and magnesium present in your hard water.